Welcome to the start of Lecture 4, where we're going to be discussing resonance. Now, resonance is a very important fundamental topic in organic chemistry, and we're going to take the time to really understand what it is, how we can understand it, and what importance it has in the units going forward. Not only in the first organic chemistry course in OChem 1, but also in OChem 2. Resonance is a factor that's going to be interfering with many different units. And if you build a strong foundation and understand what resonance is early, you'll have a lot of troubles saved down the line. So first, let me quickly, moving away from chemistry, just to talk about the basic idea of resonance. Let's get this core concept drilled in about what resonance really is. Now, this first arrow here, this is an equilibrium arrow. And this here represents equilibrium. And if we were to consider this like a chemical reaction, we would say that there's a red dot and there's a yellow dot. And the red dot can turn into the yellow dot via the forward reaction. And via the backwards reaction, the yellow dot could turn into the red dot. Hence, it's reversible. If we look at the second arrow, this is simply a forward reaction, using a straight arrow with a two-headed tip indicates that this is a reaction that really favors the red dot turning into the yellow dot. Now, where resonance comes in is where we see this arrow right here. This is the resonance arrow, and it is very important that you do not mistake it with other arrows like it. It's two-headed on both sides. We have arrows on both sides. And what this indicates in this example here is actually that the red dot and the yellow dot are two separate forms. We could call this form 1 and form 2. And the interesting thing is that neither of these forms actually exist. The red form doesn't turn into the yellow form. The yellow form doesn't turn into the red form. Neither of them actually exists. The true molecule is the resonance hybrid, a mixture of the two forms. Now, when we get into the chemistry of it, it'll get a little more complicated, but this is the core concept, that these two arrows will never indicate. Right? A resonance arrow indicates the blending of two forms to make a hybrid. Sometimes these hybrids are a perfect mix, like we see here, where the red and yellow mix to form orange. But hopefully this sets the stage for what's to come and how we're going to apply this to molecules. So when we're applying this to molecules, I first need to define this term loosely held electrons, is how I like to word it. And these are electrons that are high in energy and reactive. Generally, they are able to move, is how we can view this. And so the two types of loosely held electrons that we'll be discussing are lone pairs and pi bonds. And so when we look at a molecule, we can have this understanding that the lone pairs and the pi bonds in that molecule could potentially move around. However, they don't get to move around without any restrictions. We have two rules that need to be followed for these electrons to move. Rule number 1 is pretty straightforward, but you are not allowed to make or break any single bonds. Another way to view this is the sigma bond from hybridization. When you're making resonance forms, this is a very crucial rule. You're not allowed to make or break any single bonds in the process. The only thing that can move are the loosely held electrons. The second rule kind of goes along with the first, but I like to spell it out discreetly, is to say that the electrons you move must have a good home. Now, what I mean by this is that we're going to be able to move electrons, but we can't just move them somewhere that it's not possible to move them. We need to, if we're going to be moving the electrons, we must be able to put them in a good final place. As you'll see, this might mean multiple arrows in the same molecule, which push the electrons from one step to another step to another step to finally a good final acceptor. But with these two rules, we're going to be able to go forward and look at the first example of resonance that I think is very instructive. Now, before we do that, let's ask, why do we even care about resonance? Well, first of all, it's very important for test marks. So clearly, if you're in organic chemistry, you want to do well in the course. Not knowing resonance isn't just going to hold you back on the resonance unit. It's also going to hold you back on every unit going forward that resonance shows up in. It's one of those things like carbon or oxygen that if you don't understand right away, it's going to bite you later. So it's important for test marks. But I'd say the most important thing about resonance is that resonance stabilizes molecules. To my knowledge, there's no example of resonance in this course which will ever be destabilizing. Resonance is always a good thing. Resonance stabilizes molecules. Now, I'll be a little more specific there, and I'll say that it only stabilizes charged molecules and radicals, which is a little add-on for much later in the course. For now, I want you to understand that it stabilizes charged molecules. So, awesome. Resonance is a stabilizing force. That's probably the most important takeaway from this unit. But let's take a look at one of the most common mistakes that students make when they initially learn the rules that I've applied. So remember that the loosely held electrons, the LHEs, are your pi bonds or your lone pairs. Looking at this molecule, you may be asked, does this molecule have a resonance form? Now, if we look for the loosely held electrons in this molecule, we can clearly see that there is a pi bond, and that is between atoms 1 and 2, or carbons 1 and 2. And that is the only loosely held electron available. So the question is, can it move somewhere? Now, this is what many students are going to do. They're going to use a curvy arrow to indicate the movement of 2 electrons, and we'll move the pi bond to between carbons 2 and 3. What we'll do here is use a resonance arrow to indicate that we're talking about resonance forms. Ideally, we're only moving the pi bond, and this leads us to something that looks like this. Excellent. So we've moved a loosely held electron from, or more specifically, a pair of loosely held electrons from the bond of carbon 1 and 2 to the pi bond between carbon 2 and 3. Take a second and see if you can find a problem with this resonance form. Now, this is actually unacceptable, not good. And the reason for that has to do with a rule violation. As a reminder, we have 2 rules. We're not allowed to make or break any single bonds. So it didn't look like we broke any single bonds here. Right? This is where many students will make the mistake saying that these look like good resonance forms. However, what isn't drawn in is the hydrogens. So keeping in mind the correct number of hydrogens for each position, let's draw them in now. So the first molecule looks pretty good. Now drawing in the second molecule, remember that these hydrogens are connected via single bonds. Since they're connected via single bonds, we are not allowed to move them whatsoever. With that in mind, we have to draw them here the same way they are in the initial molecule. 2 on carbon 1, 1 on carbon 2, and 3 on carbon 3. So maybe now it's more clear why there's an issue here. Carbon 1 is actually missing. It's lost its bond electrons and gained nothing in the process. Carbon 1 has actually gained a positive charge. Carbon 2 is still okay, and carbon 3 has 5 bonds to it. We can refer to this as pentavalent, or a pentavalent carbon. As we discussed in the hybridization unit, carbocations are possible. They are definitely not stable, but a pentavalent form of carbon is absolutely unacceptable. And for that reason, this resonance form does not work. We broke the rule. right? This, in a sense, we couldn't move the hydrogens, and that means that this carbon-3 is not a good place to put those electrons. There's not enough room there. But the remaining question stands. Does this molecule have a resonance form? And in fact, it does. Now, to understand this resonance form, we can realize that we can move this pi bond not to another bond, but simply to one of the atoms. Let's say we move this to carbon-2. So using this curvy arrow indicates that the 2 electrons of our pi bond are now moving onto carbon-2. The resulting resonance form looks something like this. Carbon-2 has now gained the red lone pair. The 2 electrons that were in the pi bond have moved to become a lone pair, and thus this carbon becomes negative. Carbon-1, on the other hand, lost the pi bond. It lost its electrons, but gained nothing, meaning that it will take on a positive charge. Now, again, carbocations aren't stable. This here is a carboanion, and that's also not stable, but we didn't break any rules with resonance. This is an acceptable resonance form. So, indeed, this molecule does have a resonance form. In the units to come, we're going to discuss how this resonance form isn't the most important, and really solidify the idea that we care about resonance the most when we're stabilizing a charged molecule. So with that in mind, we're going to move forward to lecture 4.2 and discuss resonance for the stabilization of positive charges.